Now, this natural radioactivity of isotopes like uranium and potassium-40 is really too weak to be a useful energy source. There's actually a lot of energy in them. The trouble is it's released too slowly. It's released over billions of years, so the power up you're getting is really too small to do anything useful. Some of the decay products like radon or radium are rather better, but there's very little of them because it's only a brief stage in the decay of the uranium. So, not a useful energy source. Scientifically interesting, but not useful. Is there some way we can get these fissile materials to split up much faster so they can actually generate like whole watts or kilowatts or megawatts of electricity over a day rather than a million years? Well, there is, and it was discovered in the 1930s. It turns out that for certain of these nuclei, not all of them, if you get a nucleus that would normally split maybe once every 700 million years, like uranium-235, but you hit it with a neutron, the neutron can stimulate it to split and make it split right away. Okay, so that's all good. You could take some uranium and bombard it with neutrons and get it to fission much faster. But how do you get the neutrons? The normal way you get neutrons is from the radioactive decay of something. But it turns out that some of these elements, like uranium-235, when they split, as well as producing two large chunks with roughly half the nucleons, also produce typically two neutrons. And so those neutrons themselves, produced initially by the natural radioactivity, can then hit other uranium-235 nuclei and cause them to split, producing two more neutrons, which go out and hit two more uranium-235 nuclei, and so you can get exponential growth, where the natural fission of the first nucleus then stimulates the emission of two more, which then stimulate the emission of four more, then eight, and so on. And in an astonishingly rapid time, they could all fission, liberating all the energy that would normally take hundreds of millions of years in a fraction of a second. So this is a chain reaction. What are the requirements of this? Well, you need the right nuclei. The most common the right isotope. The most common isotope of uranium is uranium-238. That's because it has a longer half-life, so more of it has survived. But uranium-238 doesn't do this. You need uranium-235. Initially, the Earth had quite a lot of it, but with a half-life of only 700 million years, the vast majority has decayed long ago in the 4.6 billion year history of the Earth. There's only a tiny fraction of it left. Currently, about 0.7% of uranium is 235. And you normally have to concentrate it because the neutrons it emits, if they just hit something that's not going to split, like uranium-238 or any other rock around, that's wasted. And you need, of these two neutrons released, you want at least one, and ideally more than one on average, to hit and cause another 235 uranium nucleus to fission. So you've got to have the right chemicals. It's got to be a big enough mass that most of the neutrons will hit other uranium-235 nuclei. A small mass, most of them will escape out the side, so there's a critical mass, as it's called. And you can also use things like reflectors around. So the right sort of uranium, a critical mass, and not too many other chemicals in there that mop up the neutrons. And then you can get a chain reaction. And it turns out this has, in the Earth's history, happened quite naturally. It couldn't happen naturally now because there's not enough uranium-235 left, but in the distant past, say 2 billion years ago, it happened in what's now Oklo, Gabon, West Africa. Back then, that's about 3 half-lives of uranium-235 ago. That means there's 8 times more uranium-235 back then than there is now. So that was enough that in this underground area, water trickling through pores in the rock managed to concentrate enough uranium, which had this extra 235 uranium, enough that on average a neutron from each fission would hit another one. And so you've got a chain reaction which can still be seen in terms of changes in the isotope ratios in these rocks today. But the most famous case of a chain reaction is, of course, an atomic bomb. This is the little boy bomb that destroyed Hiroshima, the first atomic bomb ever dropped in war. And what it had was uranium-235, a cylinder of it down the bottom and a ring up the top. And explosion forced this ring down around the cylinder at the bottom. Both by themselves below the critical mass, but when you combine them together it was above the critical mass, and therefore you got the chain reaction and the whole thing exploded. They had to be merged very quickly. If you gently slid them next to each other, only a little bit of it would fuse, blowing the rest together. So to get an actual explosion, you have to put large amounts together really quickly before it has a chance to blow itself to pieces. The first North Korean nuclear test, for example, had a very low energy yield, and almost certainly their bomb blew itself to pieces before most of the uranium could fuse. Even in this case, only a few % of the uranium actually fissioned. And it was dropped on Hiroshima, and it killed, estimates are very uncertain, but probably about 100,000 people. Horrible deaths by burning. Most people were not killed by the radiation, they were killed by the blast wave and the firestorm, because if you were close enough to get a lethal radiation dose, you were almost certainly close enough to get killed by something else first before that radiation dose killed you. But it was absolutely horrific.